Okay. Hi everyone, my name is Alex, and I'm here to present digging into the core of boot. So originally this work was done by two people, myself and Yuri Buligin. Recent years we published a lot of research related to system firmware, different vulnerabilities, attack vectors, and we even released the open source framework which you can use to test your own system firmware. But a lot of that research was focused on UEFI-based firmware. And we were thinking about, okay, can we apply the same attack vectors, the same methodology to analyze different system firmware? And one of the popular another system firmware which I will talk today is a Coreboot. And I will go to some of the introduction of the Coreboot and the attack vectors which is applicable to the Coreboot compared to the UEFI-based BIOS. Then I will go and recap some of the vulnerabilities which we disclosed this year for the UEFI-based BIOSes, and then show how to apply the same vector to the Coreboot firmware. Then I will go through some of the new vectors of attack, ACPI GNVS pointer issue, which is applicable just to Coreboot firmware. And then I will go to some of the classical SMI handler issues, and will explain how this can be applicable as well for the Coreboot, because we previously presented in 2015 and 16 how does it applicable for UEFI-based BIOSes. And then I will finish with some of the small explanation of write protection functionality for the Coreboot and go to the conclusion. So initially, Coreboot was designed and developed as an alternative firmware, alternative open source version of the firmware. There was an era when there was a legacy BIOS, and legacy BIOS basically is based on interrupt table, and all of the functionality is going through the interrupt table. And there was no standard at that time for the legacy BIOSes, and then at some point the open source community figured out they don't want to have the proprietary BIOS, they want to have open source BIOS, and they try to develop the initial version of the Coreboot, call it Linux BIOS. And then they renamed it to the Coreboot. It is not really true that it is full open source, because it still uses some of the binary blobs provided by vendor during the build when it is built for the specific system. For example, MRC code, which is released from the Intel and other vendors, the code which is necessary to run during the boot time to train the memory, that code is not open source, but it's still part of the package with the Coreboot. So when we're talking about Coreboot, Coreboot has the core functionality which is open source, but it still uses a lot of binary blobs from the vendor, which is not open source. Then Coreboot grew a lot, and then they added a lot of architecture, x86, ARM, MIPS, and so on. Mostly Coreboot wrote in C. Same as UEFI-based BIOSes, there is a big code base written in C. And then there is some assemblers when you need to access specific interfaces like MSR, I/O ports, PCIe ports. You need to use some assembler functions. Then also Coreboot support ACPI standard to propagate the data from the firmware to the operation system, and as part of the implementation it uses as a language as well as UEFI-based BIOSes. Then also Coreboot support multiple payloads. Payloads, it is in the UEFI-based BIOS same as bootloaders, but just different terminology. To boot different OSs like Chrome OS, Linux, and so on. Some of the payload has specific functionality like verify boot. Some of them more like a grab, which is just booting the next step during the flow, during the boot flow. So and some of them they even UEFI-based like Tiano Core. Also, interesting fact that nowadays Coreboot is really similar in the perspective of the modulus with the UEFI-based BIOS. So that was not me. Someone there. So there is specific modulus which is defined and initialized functionality for CPUs, for chipset, and for SoCs. And then when you added the new platform, you just need to combine this modulus and add something which was not defined there. So it's not that hard. Why I mention this? Because when the UEFI create a standard, they actually specify all of these modulars. And in UEFI, you have the specific phase which is have standard, and these phases should be implemented in specific sequence. And all of that standards, it was created to make as simple as possible to develop the BIOSes and make good modular structure. Then you can reuse a lot of code, and you don't need to every time create a new code. You can just combine the components from already existing modulars. So in this perspective, they are really similar, except the Coreboot doesn't have standards. So they have good structure, but it's not kind of written in some standard way when everyone should follow it. So everyone can make any changes. And also Coreboot support verify boot, which is rooted to the hardware protection, which is one of the topics which I've explained today. So a little bit about boot flow and how does it done in a Coreboot. First, when the system is power on, first instruction which is executed is reset vector, which is fetching directly from the SPI chip. Then it calls it the boot block, which is basically the really small piece of code which is running in a mode cache as RAM. And that mode is actually using cache as main memory. It doesn't use the main memory at all. Why? Because the main memory is not initialized yet, so we cannot run from the main memory. We can run it just from cache. So what happened in this stage? In this stage, it just called the next step, which is called a var stage. Boot block doesn't check the var stage, so there is no validation or signature check done yet. So var stage is the really small stage, but the main goal of this stage having the verification functionality first. And before it has this functionality, it's supposed to initialize necessary components to have that verification method. So it is initialize TPM, SPI, and vboot, verify boot. So after they initialize these three modules, they can run the vboot and check the next step in a boot sequence. And then they check in the ROM stage and switching the execution to the ROM stage. ROM stage basically training the memory, including SPD, loading the microcode, preparing everything, preparing system to run the firmware from the main memory. So then it verifies the RAM stage and switching execution to the RAM stage. RAM stage basically making the main initialization flow for the platform. So it makes enumeration of the PCIe interfaces. It makes the SMM initialization, including SMM logs, setting SMM logs, option ROMs, ACPI table, so on. The RAM stage supposed to implement in specific sequence as well. It didn't show in this picture, but to messing up the sequence inside this stage may allow attacker to to trigger some vulnerability. For example, if the PCIe device is already enumerated, but SMM not locked yet, the PCIe device can send the DMA transaction and override the SMRAM memory and make some installation of the backdoor to the SMRAM. So RAM stage verify the payload and switch execution to the payload. Payload basically finishing the initialization, including graphic initialization, AC initialization, and it verified it called the verify kernel, which is continuing the boot of trust to the up to the application level. So as we see here, we have an entire root of trust, which is starting somewhere in a boot block and a var stage. But how does this two stages protected. So can attacker override it? So it's supposed to be read-only memory. So all of these stages is the part exist in a SPI chip in different modules in different regions. But the two of them, boot block and var stage, supposed to be just in a read-only SPI section. So meaning that it's supposed to be somehow protected. And then if you have read-only memory, which is verified read-write memory, if you trust that read-only memory doesn't have any vulnerability, you have the entire boot of trust. That's the idea. Let's see how does it implement and what kind of issues it may have. So Coreboot is just a firmware, but someone need to use this firmware to the system. So someone need to build this firmware and flash it to the system. And one of the examples is Chromebooks, which is using the Chrome OS plus Coreboot. So basically, in Chromebook, you have the Coreboot, which is basically verifying the Chrome OS component and building the root of trust from the hardware-protected SPI, read-only SPI section up to the application level. In this picture, we'll see that there is two different again, there is read-only memory, read-write memory. In read-write memory, we have the two different flow, kernel A and kernel B. It is kind of it was designed in a way that if there is some corruption happen by mistake, there is the backup flow which will restore the original one if there is original one corrupted, and the system still will boot. But because read-write memory is read-write, attacker can override it and corrupt entire stack up to the read-only memory. What happened in that case? The system will go to the recovery state mode, and in recovery mode expected that you have a USB stick which you plug in the system with the image which is signed by the vendor, and this image will be checked by read-only component and will restore entire state to system for the next reboot to boot the normal boot flow. That's kind of the way how the system is not breakable because they always can restore it. Another interesting thing is when you boot in the normal flow, you also allow to boot in developer mode. In developer mode, when you go in from read-only to read-write stage, the signature verification is not required, and you can boot your own kernel and your own payload and boot your, any operation system which supported by that payload. That's the way how you can boot, for example, Ubuntu in Chromebook system. A couple words about Verify Boot. I already mentioned almost all of the statements. We have root of trust, which is started from read-only memory verify read-write memory, which will verify the verify kernel, which will verify the rest of the system. And we can disable verify boot, go into the developer mode, and I will explain what the difference in the perspective of the state of the system, these different modes. So in the perspective of the system, before it go to developer mode, it erases entire state to making sure there is no data stored in TPM or hard drive. So when you go into the developer mode, your system is not checking the signature, but system not supposed to have any data, sensitive data from user. So why we interested in going to developer mode? Because we want to run our tools to investigate the hardware of the Chromebooks and Coreboot, and to run that we want to run Linux, and in Linux we want to run all of the variety tools which we have, like flash ROM, chipsec, and so on. And also we want to have run other tools as well. So developer mode allow you to run the run commands from the root privileges and set up options like do not check signature, run from external, boot from external device, and boot with legacy payload. What this means? It means that you allow system boot from USB stick with MBR-based system, which is basically any bootable USB stick, for example, Ubuntu. That's the way how you run the Ubuntu. And then after you run the Ubuntu, you can run the commands like flash ROM, to check what kind of protection is enabled, and to dump, for example, spy and make an investigation of the system. So one of the things which I already mentioned is there's physical protection for the read-only section of this SPI chip. What this means is, so there is a specific pin in a SPI chip, call it WP, or write protect, and this pin, if this pin is asserted, it's not allowing to modify one of the registers, calling status register. And the status register stored configuration, what kind of region should be read-only, and it's supposed to be enabled this protection or not. So basically, if this register is configured in a way that, hey, let's lock the last 2 megabytes in a SPI chip, and then you physically asserting this pin, then the SPI chip physically protecting that region, making just that region read-only. So any write transaction will not go through by these methods. So if you want to bypass it, you need to find a hardware issue or deassert this pin, and then you will have the full access. That's the basic method how the Chromebook system protecting the read-only section in a SPI chip, which is root of trust to entire boot flow. And basically, in every Chromebook, there is a screw which is asserting this pin. And if you want to open entire SPI, you need to unmount the Chromebook, find that screw, unscrew that, and then when you deassert the pin, then you will have the entire access to the SPI. But that's the basic method how this read-only memory part of the SPI chip implemented in the system. So when you boot your Ubuntu in a Chromebook, now you can run flash ROM or chipsec and dump entire SPI content, and the SPI content has some of the blocks, and then after you kind of parse these blocks, you can figure out which one is read-only, like this part is specifically read-only memory, which include GBB is a Google boot block, and then configuration, memory layout, and so on. So this memory, you cannot modify it, but you can read it and you can analyze it to verify, like, okay, how does it relate to open source version? What kind of Chromebook was installed here? Is it following all of the stages as it's supposed to be, and so on? So you can verify the entire boot sequence from here. Also, you can check the SPI descriptor to see what kind of protection SPI descriptor has. It doesn't really important because it has physical protection, but it still gives you some information about the system. Then you can dump and see all of the read-write region, including the V block for V block A, V block B, all of the structure. And then after you decode all of that, you may be able to find the SMI handlers and all of the runtime component which is necessary to analyze for understand the Coreboot in the system. You can load this in IDA and make an analysis much deeper. So I was explaining a lot about the boot flow and the component of the Coreboot and so on, but what happened at runtime after all of this boot flow is done? At runtime, the system has some similar vector attacks as UEFI-based BIOSes, because it has SMM mode. As we know, like there is ring 3, ring 0, and SMM, and you can make a privilege escalation from the ring 0 to the SMM and install some backdoor which will allow to exfiltrate data, send the data, and so on. So at runtime, the Coreboot has SMM, and if it has SMM, it should protect it properly. And all of the implementation of SMM should be done without issues, because if there is any vulnerabilities there, it can be exploited. And I will go through some of the vulnerabilities which we disclosed this year. This concept of this vulnerability may be applicable to different architecture or different firmware. Let me just explain it a bit. So then normally when you have some device, the layout of the physical memory look like this. So you have the operation system memory, you have the SMM, and you have MMIO region. Any transaction to the MMIO region going to the device directly. So the memory controller know, okay, so this is MMIO of the specific device, and I need to send transaction back to the PCH or to some other buses to the device. That's the normally what happened. And the address where MMIO range should be is stored in PCIe config space. So in the PCIe config space, there is something which is called MMIO bar, which is contain the address of the MMIO region for specific device. And when you enumerate all of the PCIe devices, you can enumerate and find all of the MMIO regions for all of the MMIO devices, for all of the PCIe devices, and then see where it is. Everything is going really well until someone is not reallocating this MMIO bar. Because some of the MMIO bar is not locked, they can be reallocated at runtime from the operation system or malicious driver. And this malicious driver may reallocate the MMIO bar and overlap it with SMM. And then after it overlaps with SMM and device send transaction, it will not go through because there is a protection called a TSEC, which is not allowing any DMA transaction going to the SMRAM memory. But some of the SMIs using the bars inside their own code. So basically, if you overlap in the MMIO bar with SMM and trigger some of the specific SMIs, SMI is not checking that MMIO bar was relocated with SMRAM, and then they just can simply read and write from there. And there is no protection from this type of access. What's supposed to be is that SMM code should check that after it reads MMIO bar, it should check, okay, where is the address located, and does it overlaps with SMRAM or not. So why I mentioned that this type of attack may be applicable for other type of firmware or other architecture, because basically every time when you have a reallocatable memory region and you have different privilege level, you always can overlap it with more privilege level and see how does memory manager manage this or how does firmware manage this. So we found this type of issues, and the multiple instances was exist in UEFI-based BIOSes. Nowadays, many of them was fixed. One of the most dangerous one was a spy bar, because that one has a lot of controls when you can overwrite a big portion of the memory, which allow attacker make more reliable exploit. This example is in a Coreboot code. Basically, what is happening here is when you increase and decrease brightness in the screen, you trigger SMI. That's by the way, typical use case for the SMI handlers and typical use case for the SMRAM. So when you need to implement some of the hardware functionality and communicate back to the operation system, the SMM is perfect location to implement that. So every time when you decrease or increase brightness, this SMI handler is triggering, and it writing to specific, it increasing a specific offset from some of the MMIO bar. And when it increases this value, basically attacker may control it and change the value of some specific register. Then when the attacker will reallocate it to different location, he has limited write primitive when he increasing some of the value by 10 hex. The biggest problem with exploiting the MMIO bar issue is that MMIO bar should be aligned. What this means, if the MMIO range size, for example, 4K, the MMIO bar should be aligned on this size. And because of that, you don't have the read primitive for any random address. You have just granular for each, for example, 4K writes. It still allows you to try to find some of the location when you can mess around with the instruction or with some tables, or with if you catch some address that will be exploitable, or yes. So that was the idea about how we can apply the methods which we disclosed in UEFI-based BIOS to Coreboot BIOSes. I will explain some new one, which is just applicable for the Coreboot firmware. So it called ACPI GNVS pointer issue. When I was mentioning about SMM and that SMM is used by the Coreboot, I didn't mention how does it use it. So in UEFI-based BIOSes, there is a bunch of SMI handlers, and all of that structure, how does these handlers enumerated, is defined in the SMM dispatch manager functionality, and it has default handler which will enumerate all of the handlers and so on and so forth. In Coreboot firmware, it has almost similar structure, except it doesn't have that much SMI handlers. So as you see, there is kind of 10 SMI handlers, and that's it. In a UEFI-based BIOS, it can be hundreds of them. So what happened when the SMI handler is triggered? There is started with flow handler start, which is setting the lock, and then will enumerate all of the CPU SMI handlers. After it finishes with all of the CPU SMI handlers, it will check what kind of north bridge SMI handlers it has. Then, for example, graphic SMI handlers. And then it go to south bridge and enumerate all of the south bridge SMI handlers, including the advanced power management controller, including memory controller, including periodic SMI, sleep SMI, and so on. So that's the list of SMIs, and it checks, okay, which one which one operation system or hardware want to execute. But there should be a mechanism how to communicate from the operation system to the SMM. And in UEFI-based BIOS, there is COM buffer, and there is a couple other methods. In Coreboot-based BIOS, there is this communication method done from global NVS. Global NVS and non-volatile storage is the structure which is used in both sides from the operating system and SMM to pass some data between this privileged level. So as you notice, because this is the input buffer for the SMM and can be attack vector for the SMM code in Coreboot. So this GNVS contains some of the fields, including the SMM interface buffer, C logs, thermal data, fan data, even Chrome OS vboot data. The pointer to this structure can be located in two different locations. One location is ACPI table. DSDT table may contain the pointer to this structure. It is implementation specific, so it may be done just by ACPI table and can be done by some other methods. And I will explain what this method is. But basically, the main idea, you have pointer to this structure. That's the main idea of this structure. How to find this structure? When we run the core info tool in a Coreboot, we can basically figure out all of the tables, system tables, the tables which is Coreboot used during the boot time and back when it communicated to the operation system from the SMM mode. So after we dump the table with address BFF1A, we can find the CPI tables and CBMEM. CBMEM is specific storage which Coreboot use to store some sensitive data, system sensitive data like some pointers for some structures, sleep state configuration, and so on and so forth. So as we see here, we having that we are locating the GNVS in CBMEM memory. So CBMEM memory contain somewhere in CBMEM memory manager somewhere this structure. Then we create the structure, the field of the structure. Then next one is we create a pointer to that GNVS structure and store that pointer back to the same storage. So CBMEM, one of the structure in CBMEM will contain that pointer, and then we create another pointer in a ACPI table for this structure. So to find this structure, we can just dump the ACPI table, decode it with ISL utility, find the address of the NVCA variable, and then we can dump the structure. From different perspective, as I already mentioned, that there is another pointer which is storing in the same storage, CBMEM storage, and this is in-memory database, that name of the storage, when the pointer to the structure is stored as well. So then we can find that pointer from that structure as well. As we see here, there is the IMD storage ID, which is giving us a GNVS value, and we see the same, the offset, there is offset to the same address as we saw it previously. So that's the main core of the problem, which I will explain later, but the main idea is there is a pointer to that structure which is in regular memory, which is not protecting and accessible from any ring 0 attacker. And then what happened next? A little bit before that. So why are we interested in GNVS? GNVS, they're allocated during some of the earlier boot stages, and the pointer of that pointer, which I mentioned already, will be used later in SMM code to some of the read-write primitives. Let's see that code a little bit. So when we have, when the system go to sleep and waking up, system need to restore the state. And when the system is restoring the state, it's supposed to initialize all necessary registers and all of the necessary structures, including ACPI tables and all of the necessary structures for that. So in this specific example, we see that during the S3 resume, it called the ACPI resume flow, which basically running the function ACPI resume, which is try to find the pointer to GNVS structure in CB memory, and then it passes this pointer to SMN setup structures function, and then it just calls reset vector. And then this SMM setup structure just triggering SMI and passing this pointer, GNVS pointer, to the SMM. And then in the right side, we see that this pointer is reading in SMM flow from the CPU state, from the register RBX, as it was passed through in the left side of the picture. And then we have this pointer in SMM code. And this pointer is not validated, and controlled fully from attacker, and this pointer in SMM code somewhere. What problem we have in here? The problem is that attacker fully may control this pointer, and attacker fully control all of the stage, how this pointer should be passing to the SMI handlers. Because attacker may force system go to S3, attacker may trigger SMI handler and replace the pointer. And in this case, as we see in this example, that attacker may be able to have the right primitives when he write to the structure, to this GNVS structure with the specific offset. Unfortunately, this primitives is not full primitive. It's not arbitrary primitives. When you control an address and value, you just controlling the address here, but you're not controlling the value. And in many cases, you kind of having even precondition, as we have in here, that first of all, precondition is telling that it may flip dword 32 to dword 0. So it will not make any random changes. It will make just some specific changes. It is really limited, but still may be exploitable if there is some configuration register or some offset stored in some sensitive structure in SMM code, which has high probability, for example, in CPU safe state area or something like this. Conclusion about this specific vulnerability, that attacker may control that pointer GNVS PTR. Also, attacker may have the limited write primitive when it flip 32 to 0 or 99 to 0. This type of issue may not be applicable if the system doesn't have a S3 boot script, or if because this vulnerability is implementation specific, some of the platform may not store the pointer to the structure to the CBMEM memory. So some of the system is more vulnerable than another, and specifically like Broadwells, they may have that vulnerability. What kind of mitigation we can make? So first of all of the pointer which we'll take from the ring 0, we should validate in SMM code. So when we implementing the Coreboot BIOS, the developer should have the checks every time when every pointer, or if there is structure, every field of the structure should be checked that it's not overlapping with SMRAM. And interestingly, that the similar vulnerability we disclosed in UEFI-based BIOSes in 2015, when we demonstrated that there is similar method called COM-buffer, which is basically was not checked by SMM, allow you to overlap with SMM code and override and make a privilege escalation from ring 0 to the SMM. Another way how we can protect from this type of vulnerability is just to have an extra copy of the address for the GNVS somewhere in SMRAM. Because this is the global structure, we can have a copy somewhere in protected storage. It's not supposed to be relocatable. Then a little bit about SMI handlers, a little bit more about SMI handlers. So that was a complicated vulnerability when you need to play a lot with the complicated structure to pass the pointer, and then you have really limited primitives. But what kind of other vulnerabilities Coreboot may have? For some of the system, pretty old system, there is SMI Handler, which is responsible to handle some of the requests in the graphic memory, in GPU and MBI registers. And here we see there in this flow, the SMI handler reading specific register, and depends on the value of that register, it picking the different flow. So an attacker basically can control that value, so the attacker may execute different flow from this function. So what happening is, that was exactly the same as I already mentioned. The vulnerable SMI handler reading the MMIO bar from the PCI config space, and then having the write primitive back to that MMIO bar. So because attacker may control this MMIO bar, it may relocate it to some different location and having the write primitive, for example, to the SMM code. Again, it has some limitation to exploit this vulnerability, but it's still valuable vulnerability, and especially because it has a magic value which is using to write to that value, so it may corrupt dword of some data in SMM code, which may be useful if the attacker will catch the sensitive structure inside the SMM. But the same handler has another vulnerabilities, which is much more easy to exploit. What is happening here is that from the same register, the SMI handler read the value and pass it to the function, call it MBI call. And this value is controlled by attacker. And this value is the address of the structure. And the structure has a couple fields. So if you'll see how the MBI call will handle it, we'll see that it has a bunch of writes to that structure. So again, if we will overlap the structure with the SMM, we can have a write primitive to the SMM code. And it has much more. So that kind of was golden function because it has a lot of writes, like, and more. So that kind of the high-level idea of what kind of vulnerability is similar for the Coreboot firmware and the UEFI basis firmware, and what kind of vector is applicable for the Coreboot firmware, and why it is important to validate all of the pointer and all of the bars in every SMI handler when we implement the Coreboot, when the developer implement the Coreboot BIOS and when they build it finally and ship it to the products. So a little bit about write protection. As I already mentioned, that the entire root of trust is based on the read-only memory. And it is really good applicable for the Chromebooks because Chromebooks has this implementation and we have really good root of trust, so it is really hard to bypass verification method of the Chromebook. It's still possible to find the runtime vulnerability, but it will not make a persistent attack. For make a persistent attack, you need to bypass the root of trust, including some of the stages, including the read-only SPI stage, which is the first one. But what if we just run the Chromebook in a random system, Coreboot? What if we run Coreboot in any random system, like we just built, for example, for Lenovo X230, we can build the Coreboot and we can flash it to this laptop and run it. So interestingly, that there is no protection at all. So all of the protection which is defined from the hardware to use by software to protect the BIOS is not used at all. So basically what this means is that if you don't have that physical protection and you use Chromebook, your BIOS is open for any type of attack found recent 5 years. And here's the summary. So SMM-based firmware write protection is off, SPI protection ranges is off, all of the SPI logs is not set, SPI configuration, SMI logs is not set, SPI configuration is not logged, and SMM accessible for DMA attack. So basically all of the protection which is supposed to be set is not set. So all of the protection relying on this pin, and the pin should be asserted. If it's not like that, the Coreboot doesn't have any other protection at all. And I would say, like, who want to install the Coreboot in their own laptop? There is not too much of, yeah, I will go to that a little bit later. So, and yeah, we call it super crazy developer mode when you can overwrite entire SPI region or SMM code and make persistent installs backdoor in the SMM code. What kind of protection we have in source code, if you will check? The single thing which we found that this function, and this function basically what it's doing is, it just tells we will ignore everything and we will flip the write enable bit, because this bit is not necessary when you send the write transaction without the BLE bit. So basically, to simplify the thing is telling we will not use protection, and if someone try to enable some bits, we will just ignore it. We would ask, like, yeah, of course, but who want to install the Coreboot on the system themselves? It's kind of, they need to understand that, okay, if you install if you install the Coreboot, you take all responsibility to enable the protection for yourself. But there is also Libreboot, which is basically having in the website a description that, okay, we don't want to use any write protection at all because it's just not just for usability reasons. It's really useful if anyone can override the spy chip from the software. And there is couple companies which is taking LibreCore and just shipping the laptop with LibreCore BIOS. It's called Prism, which basically has this open LibreCore, which is you can just override the entire spy from the software. We didn't check this. We just checked the description. So it may be that they have the protection, but that's what we found in the website. Anyway, conclusion. So first of all, the code base for the Coreboot is really big and has a lot of different components. And we need to perform all of the necessary checks for all of the components which is running in SMM mode, for all of the SMIs every time when we got any pointer. Also, we need to validate the entire threat module to understand where is the attack vectors, where is all of these ACPI, GNVS pointers came from, and who controlling them. Also, we need to really understand that if we use the Coreboot in Chromebook, that's fine because it has a BP pin which is asserted and you cannot overwrite the entire region because there is read-only memory. But if you use the Coreboot in any other random system, you need to be sure and you are responsible to enable all of the necessary protection for your system firmware, for the Coreboot. And that functionality is not just one if-def. You need to actually create that functionality because this functionality doesn't exist in Coreboot implementation. That's it. I have time for questions. Seems like no questions. Okay. Second time we present this talk and second time no questions. That's fine for me.